Hi everybody, welcome to another video in linear algebra, section 1.3, vector equations. What we learned in previous section is a system of equation, and we use Gauss-Jordan elimination to solve the system of equation. Now we explore equation in different forms, in the vector form. So we just review vectors. A matrix with only one column is called a column vector, or simply just a vector. So unlike what we have in pre-calculus, Calc 2 or Calc 3, a vector usually we denote as a vector v, and now we do that as well. This is the boldface letter v, vector v. Yeah. In physics or different textbook, they might use the v with an arrow on the top to denote that it is the vector, or we can use the hat. But in this class, I will use the boldface v. And in calculus 2 or 3 or pre-cal, we usually write a vector like this. Let's say it has 3 components, a, b, and c. We write a vector in this case, but in this class, linear algebra, the vector is assumed to be a column vector. So in this case, we will write v as the column of the matrix, a matrix of just one column. So this is called a vector, and we use the notation as a column vector, or just a vector. Right. So if it has 2 entries, then we write w1, w2, and you see the boldface w for the vector regular w will be just any real numbers. Right. The set of all vectors with 2 entries is denoted R2. This is the set of real numbers square, or we just say R2, meaning it has 2 components. Each one of them is real number, and 2 vectors are equal if the corresponding entries are equal. Now instead of using the vector as a horizontal component, when we write like this, the vector now is written as a column vector. Right. The basic operation, this is just a review. If we want to add to vector u plus vector v, we just add the components, the first with the first, the second with the second. If we want to multiply a constant, a real number, into a vector, we multiply that constant to each component of the vector. So this is very straightforward. Right. Now let's u equal to vector of 1 and negative 2, v is vector of 2 and 4, find u plus 2v. So this is pretty straightforward. Vector u is 1 and negative 2 plus 2 times vector v, 3 and 4. So just like all the operation, we do multiplication first. Multiply 2 into the second vector. 2 times 3, 2 times 4. And then we add the vectors. 1 plus 6, 7, negative 2 plus 8, 6. Now, on the calculator, of course, we can add the matrix. Once again, alpha zoom if we want the matrix, but it is better we just add using a list. So you see above number 1 to 6, there's L1, L2, L3 all the way to L6. To get that, we hit second and a number, so we had the list. Right. However, if we just want to work with something simple like this, we use second open parentheses. We have 1 and negative 2. So this is not a vector, but it is just a list of 2 numbers, a set of 2 numbers, pretty much. But we're gonna add that with 2 times the list or the second list of numbers 3 and 4. So now we work as a list or a set of numbers. Again, second parentheses to open and close the bracket, the commas here. And of course we have 2 components, so we have the answer. Of course that's not in the vector form, but it works similarly. It's just a set of numbers. Right. Now do -2 times vector u plus 3v. I just want to write out what if we have to write a vector u, that's the vector u, and then 3 times vector v. Right, so it will be like that to distinguish with the regular u and v, right? So we have -2 times vector u of 1 and -2 plus 3 times vector v of 3 and 4. So multiply first -2, it was -2 and 4, and then 3 times 3 is 9, 3 and 4 is 12. That is 7 and 16. Once again, on the calculator, -2, second open parentheses, 1 comma -2 plus 3 times open parentheses, 3 comma 4, and that's what we have. Alright, so very basic geometric description of R2. Consider a rectangular coordinate system in the plane. So we have the origin, x coordinate, x-axis and the y-axis. So look like that. Each point in the plane is determined by the order pair. So the coordinate of the point A and B we write like that. And associated to that, we have the column vector A and B. And the set of all those points is also in R2. Geometrically, the vector AB can be written as a point A and B. So as you see, on the bigger picture of just a vector, of course the notation is not important. We can write like that, or just a list of numbers like what we use on the calculator. Just a vector is something that has more than one component. It doesn't matter how we write the component, stack that in a column, stack in a row. But think about vector in R2 is something that has 2 components. So we can write that as a point, or if we represent geometrically a vector, the tail end is at the origin, and the head of the vector is at the point. So in that case, every vector is associated to a point. So a point is a vector is a point, something that has 2 components, if it is in R2. Right. And this just a review. Geometrically, when we add the vectors, we can add that head to tail rule, meaning the first vector we stack the second vector, the tail of the second vector on the head of the first vector. So we go from u to v, and sum of u and v is this vector. Or we can use a parallelogram. We put both vector the tail end at the same point. We draw a parallelogram. The diagonal is the sum of the 2 vectors. Right. One thing I did not mention about the vector is that a vector has no location. So in this case, when we say the vector AB by default or in standard position will be at 0, but we can also say this vector is also a vector AB as long as the point in the same direction and the length are the same, the vector are the same. vector has no location. So we can put a vector here, there, or anywhere in the plane. They will be the same. Right. Now, let u be the vector 1, -2. So, like I said, location doesn't matter. What it means is we go 1 horizontally and -2 vertically. So, let's look at the vector u. In general, is 1 unit to the right and 2 unit down. So we can say this is a vector u. And vector v is -1, so 1 unit to the left and 1 unit up. 1 unit to the left and 1 unit up. Sorry. Right. 1 to the left, 1 up, and then 1 to the right, -2 unit down. So that is, now what we do is 2u. 2 times vector u is going to be the same vector but twice as long. So we can say, if we want to, 2 times vector u is 2 times the vector of 1 and -2. So that will be a vector of 2 and -4. And we can draw that anywhere. So 2 unit to the right and 4 unit down. So this will be a vector 2u. Right? And then vector v is -1 and 1. So if we want to add 2u, which is this, and then add the vector v, so from this point we just draw using head to tail method, for example. So we have the first vector 2u is this. Vector v is, just draw the vector v starting at the head of the vector 2u. So this is v. Excuse me. And the result is going to be 2u plus v. Yeah. So just move closer to the camera. Maybe you see. Again, 2u, and then head to tail method. I draw 2u first and then v, and that is the result. Of course, if we want to confirm it, we can just do it by hand easily. 2 times vector u of -1 and 2 plus vector v of -1 and 1. Second parentheses, -1, comma 1. Right. If I type it correctly, 1 comma -2, sorry. Right, so I have 1 and -3, meaning if you see the result, 1 unit to the right and then 3 unit down. So that is correct. Right, next, u minus v. So we have once again vector u and vector v. I just draw that anywhere. And then u minus v. So I have vector u first and the negative v will be opposite to v. So if this is v in that direction, then we can say this is v negative v. I said vector has no location, so I can draw a vector at any point. It only has direction and the length. So this is negative v. Now I use parallelogram. And the diagonal is u minus v. Of course, if we do this by hand, u is 1 comma negative 2. Subtract v, negative 1 comma 1. As you see, we have u and negative v opposite to v, and we draw the diagonal to a parallelogram. We should have u minus v. Okay, so instead of write u minus v, what I did is just u plus opposite to v, and then we can use parallelogram or head-to-tail method to add the vectors. Right, I just review. You should have this earlier in pre-calculus or Cal 2 or Cal 3. Vectors in R3 or Rn. Now we define similarly a vector in R3 will be something with 3 components. Doesn't matter if we put that in a column, we put in the angular bracket, or doesn't matter how we write it. R3 meaning they has 3 components. They have 3 components. This vector can be represented in 3-dimensional space. Once again, because it has 3 components with arrows are origin. So this will be the same. Rn will have n components. And we write a vector in Rn. It's just a column of n components. Each component is a real number. A vector whose entry are all 0 is called a 0 vector, denoted by both phase 0. So if this you write by hand, we cannot write like that, so we write that is the 0 vector. Of course, we can say a 0 vector. Either way, it has something we have to write that distinguish between the 0 vector, which have a bunch of 0 number, as opposed to a 0 number, and this is 0 vector. Right. Now these are the properties of vectors. It is associative, meaning u plus v the same as v plus u. We go from u to v and then to u to v, the same thing. If we use a parallelogram, either we have u or v, changing the order doesn't matter. We still have the same diagonal. The next one is associative. We have 3 vectors u, v, and w. It doesn't matter how we add them. We can add the first 2 or the last 2. The order will not change, but we just add the order of the addition that we carry out. Right. U plus 0 vector is the same as 0 vector plus u equal to u. So this is the identity property. So let me say this is commutative. And this is associative. U plus 0, vector u plus vector 0 is the vector u. So this is identity, additive identity. u plus negative of vector u is equal to a zero vector. This is called additive inverse, but I don't want to use inverse, that might confuse with something else. Distributive the constant into a sum, and distribute vector into a constant, and then scalar multiplication, and then a number 1 times a vector is equal to a vector u. Right. What we don't have here is a vector times a vector. In pre-calculus or in Calc 3 we have a dot product between two vectors or cross product between two vectors. We do not do that in this section. We just all the operation we have in this section, it's just addition. So we add two vectors and we multiply by a scalar multiplication. So multiply a constant to it, to a vector, or add two vectors. That's all the operation we do in this section. Right, so that's just a review about vectors. Now we have to something new. Linear combinations. Given vectors v1, v2, vn all the way to rn. Notice that this is, all the way to vp. So we might have 5 vectors in R2, or we have 2 vectors in something else. So the number here and there are not the same. Doesn't have to be the same. That's what I should say. So we have p vectors and then p constant c1 to cp. The vector y defined by y equal to c1 v1 c2 v2 all the way to cp vp is called the linear combination of v1 to vp, and the c1 to cp, those constant, are called the weights of the linear combinations. And the weight can be any real numbers, including 0. So once again, we just have the number of vectors doesn't have to be the same as the dimension of the space. Right. Now, next, we go to the first example. The figure identifies the linear combination of v1, negative 1 and 1, and v2, 2 and 1. So let me just say we have v1, negative 1 and 1. So on the picture, this is v1. And then v2 is 2 and 1. So that is v2. Now we have 2 vectors in the plane. So this vector have 2 components. So these vectors in R2. So we say vector v1 and v2 in usually we use this R2, and this symbol here meaning it's an element of that set, or we just say in. So v1 and v2 are in the set of all two-dimensional vectors. Right, so v1, v2. Now the linear combination of this, we just take a vector in any extension of that in that direction will be v1, and combination with the vector in this direction v2. So for example, if we want negative 2v1 will be this vector but opposite direction and twice as long. So negative 2v1 is going to be this. And then v2 is that 2v2, 3v2, negative 2v2, negative 2v2, and so on. Let's say if we want to go to this point, what is this vector represent? What's that vector? Right. So to get to that point, what we do is we go with the v1 direction, one step, two step. So this is negative 2v1. And then we will go v2. These vectors are the same. These vectors are the same because they point in the same direction and they have the same length. So in that case, we say negative 2v1 plus v2 is going to be this vector. As you see, given two directions like this, we can go to any point in the grid. For example, if we want to go to this point, right? First, we will go in this direction, so that we have a v, and then we will go to this direction, and that is 3/2 of v1 plus v2. So given two vectors like this in the plane, we can go to any point in R2, because that have a meaning to it later. So bottom line is, this is the linear combination of v1 and v2. This is the linear combination of v1 and v2. Of course, the weight of the linear combination can be 0, so we can say 3 times v1 is going to be this. It's also a linear combination of v1 and v2. Right. Now, right, so the linear combination is just a combination of the vectors with different weights. The weight could be 0. Right, now, let the vector a1 be this, and a2 be that vector, and b determine whether b can be generated or written as a linear combination of a1 and a2. So in that case, the question will be translated to this. Can we write is vector b equal to a linear combination? So linear combination, let's use the way as c. So it's c1 a1 plus c2 a2 equal to vector b. So if it is, then we say b is a linear combination of c1 and c2. I mean, if there is a solution, then we can say b is a linear combination of a1 and a2. Right. So that is in vector form. Notice that I distinguish the vector and the constant. Again, if you do not like that notation of the boldface, just use the arrowhead. So we say c1 a1 plus c2 a2 vector b. Yeah. But in math, usually they use the boldface for the vector. Right. Now we just rewrite this as c1 vector a1. We have 3 components: 1, -2, -5, and vector and c2 times vector a2, 2, 5, and 6. Is that equal to this vector? Right. Now, combine the vectors. We multiply c1 to all of the components of vector a1 and c2 multiplied to here. So we will have c1 minus 2c1 minus 5c1. And then the second vector, 2c2, 5c2, and 6c2. Equal to 7, 4, and -3. Right? So yeah, just combine the vectors. And now we combine the vector by just add the components. So add component, we will have C1 plus 2C2 minus 2C1 plus 5C2 and minus 5C1 plus 6C2 equal to 7, 4, and negative 3. Right? And now two vectors are equal if the corresponding components are equal. So in that case, C1 plus 2C2 is equal to 7. So we will write that as a system of equation. C1 plus 2C2 equal to 7. Negative 2C1 plus 5C2 equal to 4. And negative 5C1 plus 6C2 equal to negative 3. Right. So that's just system of equation. Three equations, two variables. So if we want to, we can put this in the augmented matrix. One, 2, negative 2, and 5, negative 5, and 6, 7, 4, and negative 3. And then just like previous section, we just use reduce row echelon form. Second matrix, reduce row echelon form of the vector, the matrix 3 by 3, 3 rows, 3 columns, right? 1, 2, 7, negative 2, 5, 4, negative 5, 6, and negative 3. All right. So we end up with that. 1, 0, 3, 0, 1, 2, 0, 0, 0. Right. Now, for the augmented matrix, we have the column for C1, the column for C2. So this is for C1, and this column is C2, and the pivot is at here and here. So we have C1. This equation, the C1 equal to 3. This equation, the C2 equal to 2. So we have C1 equal to 3 and C2 equal to 2. So because this has a solution, the equation, this equation has the solution C1 and C2. So we say B is a linear combination of A1 and A2 because there is a solution. There is a solution, so we say vector B is a linear combination of the vector A1 and A2. In particular, we can say vector B is equal to 3 times vector A1 plus 2 times vector A2 because we have C1 is 3 and C2 is 2 in particular. Right. That's what we have. Of course, then you say, that sound like a lot more work done. It actually is. And in fact, it is. If you notice that what we have here is the column vector A1 and the column vector A2 and column vector B. When we put in the romantic matrix, we just have this as vector A1, this as a vector A2, and this as a vector B. So essentially, instead of writing this system of equation all kind every step from here to there, we just said we can just put the vector A1, vector A2, and then vector B in that form. And we just do the math after that. We don't have to do all the intermediate steps to go from here to there. And that's essentially what we have in this note. In particular, B can be generated by the linear combination of A1 to AP if and only if there exists a solution to the linear system, and we write that in the romantic matrix right away. That is a better way to write. Alright, so is B a linear combination of A1, A2, and A3? Once again, this is equivalent to equivalently there is C1 A1 plus C2 A2 plus C3 A3 equal to vector B. Equivalently, there is this equation has solution. Right. So again, instead of writing out like this, we can just go and put in the romantic matrix form, which is this. Vector A1, vector A2, and vector A3. So that's why we write a vector as a column, so we can stack them into a matrix. And vector B. So which is equivalently equal to 1, 1, and 5, 1, negative 1, and 1, 1, 5, and 1. The bar, vector B, 1, 13, and negative 19. And we'll just do, they are not equal. So that's why I draw an arrow instead. So perform reduced row echelon form for this romantic matrix. Right. And we have this matrix in reduced row echelon form. Right. Now, once again, we stack the vectors A1, A2, A3, but equivalently to this equation. That's why I rewrite the problem with this, so we can write the solution. We have the variable to write the solution. That's what I mean. So this column corresponding to C1, C2, and C3, and we do have the pivot entries. So this equation C1 equal to negative 5, C2 equal to 2, and 1 C2, C3 equal to 4. Because it has a solution, so we say B is a linear combination of these three vectors. So B is a linear combination of A1, A2, and A3. In particular, vector B is a combination of negative 5 A1, 2 A2, and 4 A3. Right. So we have the vector just stack all the vector on the left side and then the vector on the right side. If it is the linear combination of those vectors, it has to be a solution. Right. Next we have this definition of span. If V1, V2 on the way to VP are Rn, then the set of all linear combination V1 to Vp is denoted by span of V1 to Vp, and is called the subset of Rn span by V1 to Vp. That is, a span of V1, V2, Vp is the collection. This is just the collection of all vectors that can be written in the form. So meaning is the set of all the linear combination of the vectors, and the scalar is that. Right. So now here is an example. So we have a space, three-dimensional space. That's what we are. We are three-dimensional space creatures. Now think about this. If we have a line, imagine an ant just moving along the line. It can go backward or forward. So this is one-dimensional creatures. It can go backward and forward on that line. That is one-dimensional creatures. Now we're going to add another vector, if you will. That is another arm. Now the linear combination of these two can generate every point on the plane, right? For example, if we have these two direction, by direction could be backward or forward along these two lines. If I want to go to this point here, I will go along this, and then I go to that side, right? So with these two directions, I can go anywhere on the plane. Think about this as video games, for instance. We have one direction go up and down, one direction left and right. With those controls, we can move anywhere in the plane, right? Now the vector doesn't have to be perpendicular. Just as we have earlier, we might have those vectors that in those directions. Any other two vectors that are not parallel can generate every point in R2. Now I did say that we are two-dimensional creatures, right? Now let's say instead we use one vector in that direction and another vector in this direction. For example, in that case, what we generate is the plane. in here, right? So we say the span of these two vectors is the subset of three-dimensional space. We have two vectors in three-dimensional space, and those two vectors combined together give us this plane right here. So this plane is span of these two vectors. Right. Here is an example. Let V be a non-zero vector in Rn, then the span V is the set of all scalar multiplication of V. So we have three-dimensional space, and the vector V, let's say vector V in this direction. Then the span of the vector V is the whole line. We can go forward and backward on that line. Likewise, if we have vector U and vector V, the linear combination of U and V, suppose they are not multiple of each other, suppose they are not parallel, then the span of those two vectors will be this plane with vector U and vector V. So the plane will be the linear, the set of all the linear combination of vector U and vector V. So if we have one vector, it is a line characterized of a line. If we have two vectors that are not multiple of each other, we have a plane. If we have three vectors that are not parallel pairwise, then we can have the whole space. So think about this. Instead of controlling an object moving in the plane, if we have one more button that go up and down, we can go anywhere in three-dimensional space. Of course, this generalization can extend to further into n-dimensional space. We are only three-dimensional creatures. But if there are a four-dimension or higher dimension creatures, we will be in trouble. Think about this. Let's say we talk about an ant can go back and forth on a straight line or anywhere on a two-dimensional space, which is on a plane. Let's say we standing here on the ground and we have an whole army of ants approaching us. We're in trouble, unless of course we can fly away, we can jump. If the whole army ant approaching us, and all we do is just jump into the third dimension to this and then walk away with no problem. So that an ant moving on a plane, so the ant move every direction on the plane is the two-dimensional movement toward us. We just go to the third dimension and escape in it. Now think about it that way. If we are three-dimensional creatures. Let's say we surrounding an alien. At this point, we might have all the tank pointing to that, and then we have airplane on the top and at the ground. So we surround an object in three-dimensional space. But if that creatures is a four-dimensional creatures, that we move to the fourth dimension creature, which we don't know where is that, and escape. So that's why I said if we have encounter a higher dimensional creatures than three, we're in trouble because we cannot surround that creatures. They just go in another dimension, the fourth dimension, and get away from us. All right, that's just a story. Usually, every time we learn about multivariables or higher dimension, you probably will hear this, the same kind of story. Right, now we have more example. I say we have these vectors and is B a linear combination, is B in the span of A1, A2. This is just the same thing as saying is B a linear combination of A1 and A2. Yeah, the question are the same. Because span will be the set of every linear combination of A1 and A2. If B is a part of that, it has to be a linear combination. So what we just said is B equal to C1 A1 plus C2 A2. Of course, we can write that out with like this, but we have a little note. We just stack this as A1, A2, and B. So we just put in our matrix matrix A1, A2, and B. So is B a common linear combination of A1 and A2? To solve that system of equation, we have that answer. Vector A1, 1, negative 2, and 3. A2, and vector B. Now let's do the linear combination. Reduce row echelon form. Three rows, 3 columns. 1, 5, negative 3, negative 2, negative 13, 8, 3, negative 3, and 1. Right. Right. So I just want to write that so we have the variable C1 and C2. Right. Now, in this matrix, we have the pivot, but moreover, we have the pivot in the last column. If we have a pivot on the last column, that means there's no solution. So if we have the pivot at the last column of a romantic matrix, last column of a romantic matrix, no solution. So if no solution, then we say B is not a linear combination. So B cannot be generated by A1 and A2. A simple version of that, or we just say vector B is not in the span of A1 and A2. Yeah, so write like this is much better than to say B is not a linear combination of A1 and A2. We just say B doesn't belong to the span of A1 and A2. Of course, that should be vectors. Now, an example of that is if we have two vectors like this, it generates the plane, but the third vector is in that direction. So this third vector cannot be generated by those two vectors. Right, more samples. For what values of h will y be in the span of these three vectors? Once again, we're going to put that in the metric matrix and see if y is a linear combination of those three vectors. So again, I just want to write something like that, so we have the C1, the variables. Notice that this is the column A1, corresponding to that is the variable C1, or the weight C1. Right, now I just want to say, for what value of h will y be in span of that? So I'm just going to write C1 V1 plus C2 V2 plus C3 V3 equal to y. Right? So I just have the variable. Alright, now let's put that in the metric matrix. One, -1 and -2, 5, -4, -7, -3, 1 and 0, -4, 3 and h. Right. Bad news is, in this case we have the variable. We cannot put in the calculator and trying to find reduced row echelon form. So we have to do this by hand. Right. So how do we do this by hand? Right, first we have the pivot of 1, which is very good. Now we're going to turn this entry to 0, and then we turn this entry to 0. Right, so the pivot is in the first row, so everything will spin off the first row. And if we want to eliminate, we're going to use the opposite number to what we try to eliminate. If we try to eliminate -1, we use 1. And then we will add and replace to the row that we eliminate, so that will be row 2. And we start to row 2. Right. I'm going to do this by hand because there's h later on. We cannot use a calculator anyway. So row 1 and row 3 will stay the same. Now row 2 will change. -1 times row 1, 1 times 1 is 1, plus -1, 0. 1 times 5, 5, minus 4. 1 times -3, -3 plus 1, -2. 1 times -4 and 3. Right. Right. So again we have the pivot here. That is 0, which is good. Now we need this to 0. To turn this to 0, we'll based on the pivot of 2, pivot on row 1. And if we want to eliminate -2, we use the opposite to that, which is 2. And we will add and replace into the row we try to eliminate. Right. In that case, row 1 and row 2 will stay the same. So I'm just going to copy row 1 and row 2. Now row 3. 2 times 1 is 2 minus 2. 2 times 5, 10 minus 7. 10 minus 7, 3. 2 times negative 3, negative 6 plus 0. And 2 times negative 4 is negative 8 plus 8. Negative 8 plus 8. Yeah. Right. So we have that check, that check, that check. First column is good. Now the next pivot is going to be this one. The next leading entry is that. Now we need to turn that to 0, that to 0. Let's just turn this one to 0 first. To turn that to 0, what we need will be spin up or based on the pivot on row 2. The pivot is on row 2. And to eliminate, we use the opposite number to the number we try to eliminate. So eliminate 3, so we're going to use negative 3, opposite to that. We will add and replace to the row that we try to eliminate. Right. So row 1 and 2 will stay the same. Now row 3. Negative 3 times 1, negative 3. I'm sorry. Multiply row 2. Okay. Of course, if we multiply to row 1, that's turned to something else. Alright. Yeah. So we have 0 here already, so it doesn't matter what we do, it's going to be still 0. So that's why we do this by column. So when we have 0, it doesn't matter what we do, it's still 0. Negative 3 times 0 plus 0. Negative 3 times 1, negative 3 plus 3, so that is 0. Negative 3 times negative 2 is positive 6 minus 6, that's also 0. Negative 3 times negative 1 is 3. 3 minus 8 is minus 5 plus 8. Negative 3 times negative 1 is 3 minus 8 is minus 5 plus 8. Now, of course, we can do the rest of the problem, but we can stop here. What we see here is the pivot is going to be here and here. This should be the pivot. However, just like what we said on the last example, we cannot have the pivot on the last column, otherwise there will be no solution. We cannot have the pivot as the last column of an augmented matrix. So in this case, the only chance for this to happen is this has to be 0. So the system will have solution, infinitely many solutions. So I will write for this to have solution. For this augmented matrix has solution. For the system to have solution, or we should say for the system to be consistent, we cannot have pivot on the last entry. cannot have pivot entry and not have pivot at the last column. If this is anything but 0, that would be a pivot. So we have to turn that has to be 0. So in that case, we do not have any pivot but those two. Meaning -5 plus h has to be 0. Otherwise, that could be the pivot. The pivot is non-zero entry, and then of course we divide by itself, we can normalize to 1. But if it is 0, we cannot turn the 0 into 1. We can turn anything to 1 by divide by itself, but we cannot turn the 0 into 1. So in order for this system to be consistent, for this equation has solutions, this entry has to be 0. So h must be equal to 5. Right. So what we learned in this section is the system of equation can be written in the vector form. And if it is a solution, then we say the vector on the right hand side is a linear combination of the vectors on the left hand side. The solution would be that particular combination of the vectors. Right. So, and of course we review vectors, but most important is about linear combination. And of course the set of all the linear combinations is going to span the vectors. And with that, we finish section 1.3. See you in another video in linear algebra. Thank you for watching.